The subject we chose for our math story is the second derivative, and the definition of that is the derivative of a function. And this can be used to provide information about a function's concavity, inflection points, and local extrema.
Physics. In physics, the second derivative can be used to describe acceleration or the rate of change of velocity. Velocity is the change of distance covered by a unit of time, and acceleration describes how that velocity changes over time. So that's how you get units of, for example, meter per second per second. Um, the second derivative is also essential for Newton's second law of motion, where force and acceleration are directly proportional to each other. And in quantum mechanics, the second derivative plays a key factor in Schrodinger's equation and represents the kinetic energy of the particle. It shows us how the wave function changes over time and can be used to predict future state um, of the system. Engineering. This slide focuses a bit more on mechanical engineering and how the second derivative can be um, instrumental in the part of the construction of these structures, especially those that have a lot of movement, like aircrafts, cars, roller coasters, lots of moving parts, because it helps us understand the combination of different factors and the stresses that they would cause. So, like acceleration, um, internal forces, and curves. So, for example, roller coasters they combine all these factors. Not only are they giant structures just within themselves, but they take you to point A, and they do so different accelerations, decelerations, hills, twists, curves, drops. And none of that would be very fun if we didn't have the ability to calculate potential points of structural failure, identify points of maximum and minimum stress, and ensuring uh, it can actually withstand that stress and strain on the structure. It also helps prevent jerk. So think of the smoothness of the ride, even in things like elevators or the movement of robots. Chemistry. In chemistry, titration is a critical lab skill slash experiment that you're very likely to perform if you do any general chemistry. Um, and it's imperative to various fields like pharmaceuticals, food science, environmental monitoring, so think like wastewater management and quality control. It's used to find an unknown concentration of a sample using concepts of like pH, acid-base reactions. Essentially, we're trying to find like the neutralization point, which is also the inflection point of the solution. The second derivative determines the titration endpoints, which allows us to more accurately locate that inflection point by finding where like the rate which the pH changes is at zero, which is also the slope being zero. So these are just some graphs. The graphs to the left are the titration curves, so pH versus the volume. This is our original curve that we're getting our derivatives from. So the graph to the right is where we get the second derivative, and it's the derivative of the first derivative for the y-axis, and the pH, like what we want, on the x-axis. So the graph is a little blurry, but in this example, like right where it crosses that at 11.3 milliliters would be the inflection point, or the point where the acid-base solution was neutralized.
The second derivative can also be applied to economics. Two examples are profit maximization and market trends. With profit maximization, the second derivative is used to verify if maximum profit has been reached at critical points. Side note, critical points are determined through the first derivative. If the second derivative is negative, there is a maximum profit, and if it's positive, there is a minimum profit. For market trends, the second derivative can be used to determine if the rate of economic growth is accelerating or decelerating, which can help investors analyze risk. We've also applied the second derivative to our majors. I am in pharmacy, and the second derivative exists in pharmacokinetics and pharmacodynamics, which is basically what the body does to the drug versus what the drug does to the body. The second derivative can be used to locate inflection points of a concentration curve, showing where the rate of change of concentration slows. So, in other words, it shows the speed of absorption and distribution. Jackie is in electrical engineering, which I know nothing about, but she said electrical engineering involves so much math that you could easily become a math major. A specific example is signaling, and shout out to Justin, who was in our class, who's a dry etch plasma process engineer who must be able to calculate the instant there is a change in an optical signal wavelength. So signaling can also involve the second derivative. And then for Ben is in computer science, and an example of the second derivative in computer science is machine learning, which uses algorithms like Newton's method to understand the curvature of an error function, and the curvature is used to find the minimum of the error function. Apart from how we use the second derivative in our society, two questions still stand. How can we use the second derivative to help us solve the most significant problems of our time? And how can we make the second derivative more relevant to our lives? I already think that the second derivative is used in a multitude of ways that help us solve problems of our time. However, another application we didn't cover is an epidemic. COVID wasn't that long ago, and the second derivative was a part of monitoring the spread of the disease and predicting the trajectory of it. For both questions, I think that being aware of and understanding what the second derivative is and its role for data can make it more relevant within our lives. We usually don't think about how our acceleration is changing when we drive a car, or the rate at which perfume diffuses in the air when we spray it. Therefore, we can make the second derivative a bigger part of our life through the continued teachings of calculus and other subjects in math.